Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It is our 7th lesson on the 9th topic of Form 3 work, which is called quantity of heat. As usual, let me commence by giving the quote of the day, which states that shortcuts cut dreams short. We shall discuss that quote at the end of our class today. So today we are looking at further examples involving quantity of heat and of course specific latent heats. So our first example reads that a metal block of mass 150 grams. So again, we convert each quantity into its respective SI unit. We know that the SI unit for mass is the kilogram, and we know that 1000 grams is equals to 1 kilogram. What about 150 grams? So that will be 150 grams of 1000 grams times 1 kilogram. So 150 divided by 1000, you'll simply obtain the mass of the metal block as 0.15 kilogram. That is in its respective SI unit at 100 degrees Celsius. So that is the initial temperature for the metal block. So initial temperature for the metal block is 100 degrees Celsius. It's dropped into a lagged calorimeter of heat capacity 40 joules per Kelvin. So we are given the heat capacity of our calorimeter as 40 joules per Kelvin, containing 100 grams of water. So we are given the mass of water. Again, we convert 100 grams into SI unit, which are the kilogram. Again, we know that 1000 grams is equals to 1 kilogram. What about 100 grams? So that will be 100 grams of 1000 grams times 1 kilogram. So 100 divided by 1000, you will simply obtain the mass of water as 0.1 kilogram. Of water at 25 degrees Celsius. So that is the initial temperature for water is 25 degrees Celsius. Again, because initially the water was in the calorimeter, it simply means that our calorimeter will assume the same initial temperature as that of water. Therefore, because the water initially had a temperature of 25 degrees Celsius and the water was within the calorimeter, it simply means that the initial temperature for the calorimeter will also be similar to the initial temperature of water, which is actually 25 degrees Celsius. Then we are told that the temperature of the resulting mixture is 34 degrees Celsius. So that is T final, or the final temperature of the mixture, is 34 degrees Celsius. Then we are told that the specific capacity of water was 0.0042 megajoules per kilogram per Kelvin. So just like we said under work, energy, power, and machines, we did say that 1 million joules will always be equal to 1 megajoule. Similarly, 1 million joule per kilogram per Kelvin will always be equal to 1 megajoule per kilogram per Kelvin. Therefore, to convert 0.0042 megajoule per kilogram per Kelvin into the SI unit of specific capacity, which are the joules per kilogram per Kelvin, I'll simply say that if a million joule per kilogram per Kelvin is equals to 1 megajoule per kilogram per Kelvin, what about 0.0042 megajoule per kilogram per Kelvin? So that will be over 1 megajoule per kilogram per Kelvin multiplied by 1 million joule per kilogram per Kelvin. So to convert 0.0042 megajoule per kilogram per Kelvin into joules per kilogram per Kelvin, you'll simply multiply 0.0042 by 1 million. Therefore, if you take 0.0042 times 1 million, you'll simply obtain 4200 joules per kilogram per Kelvin, which are the SI unit for specific heat capacity. Then we are told that determine the heat gained by the calorimeter. The heat gained by the calorimeter. Now, for the calorimeter, we are given the heat capacity. From quantity of heat lesson 1, we did say that we did define heat capacity as the quantity of heat required to raise the temperature of a given mass of a substance by 1 Kelvin. So that simply means when we talk of heat capacity, we don't put into consideration the aspect of mass, because the mass is not specific. It is only for specific heat capacity that we include the mass in our equation. So under the same lesson, that is quantity of heat lesson 1, you can just check it from this channel. We did say that the heat capacity, the formula for heat capacity will be the quantity of heat Q divided by the change in temperature, which is in Kelvin, that is theta. So that means that if you want to find the quantity of heat given the heat capacity, from this formula, Q will simply become, I'll simply multiply both sides by theta, therefore Q will be given by C multiplied by theta. Of course, where capital C stands for heat capacity, and of course theta stands for change in temperature. Therefore, the heat gained by the calorimeter will be given by C theta. So I'm using C theta because for the heat capacity, I'm given, that is for the calorimeter, I'm given the heat capacity. Otherwise, if I was given the specific capacity of the calorimeter, I could have used the normal formula, that is MC theta. But because I'm given the heat capacity, Q will be given by C theta. So we ignore the aspect of the mass of the calorimeter. Therefore, the heat gained by the calorimeter will be given by C theta, or the heat capacity of the calorimeter multiplied by the change in temperature of the calorimeter. So the heat capacity of the calorimeter we are given as 40 joules per Kelvin. So that is 40 multiplied by the change in temperature for the calorimeter. We'll simply take the initial temperature for the calorimeter, we subtract from the final temperature of the mixture. So T final was 34, initial temperature for the calorimeter was 25. Therefore, the change in temperature for the calorimeter will simply be 34 minus 25. So 34 minus 25. So of course, if you take 40 multiplied by the difference of 34 and 25, you will simply obtain 360 joules. So that is the heat gained by the calorimeter. Then Roman 2, they want us to find the heat gained by water. So because for the water, we are given the specific heat capacity, it simply means that Q for water will consider the aspect of mass. Therefore, the heat gained by water will be given by mass of water multiplied by the specific capacity of water multiplied by the change in temperature for the water. Remember, if we were given the heat capacity of water, we could have just used C then theta. We could have just taken the heat capacity for water multiplied by the change in temperature for the water. But because we are given the specific heat capacity of water, we'll use the formula. We have to include the mass in our equation. Therefore, the heat gained by water will be equal to mass of water multiplied by the specific capacity of water multiplied by the change in temperature for the water. So the mass of water we were given as 0.1 kg. So 0.1 multiplied by specific capacity for water, we have just found it as 4200 joules per kilogram per Kelvin, times the change in temperature for the water. We'll simply take the difference between the common final temperature, which is 34, then we subtract with the initial temperature of water, which was 25. Therefore, the change in temperature for water is 34 minus 25. So if you take 0.1 multiplied by 4200 multiplied by the difference of 34 and 25, you'd simply obtain 3780 joules. So that is the heat that is gained by water. Then Roman 3, they want us to find the heat lost by the metal block. Now notice that in this case, it is only the metal block that is losing heat. Why? Because if you look at the initial temperature of the metal block, is far much greater than the final temperature of the mixture. So because the initial temperature for the metal block was 100 and the final temperature for the mixture is 34, it simply shows you that the metal block lost heat. That is from 100 degrees up to 34 degrees Celsius. But the calorimeter and the water, they were both initially at 25 degrees Celsius, but the final temperature is 34. So if a substance has an initial temperature which is less than the final temperature, it simply shows that that substance gained heat. Therefore, we can conclude that both the water and the calorimeter, because they were initially at a lower temperature and the final temperature is 34, which is higher than 25 degrees, it simply shows you that the calorimeter and the water, they both gained heat. So the only substance that is losing heat is actually the metal block, because its initial temperature is far much greater than the final temperature. So the initial temperature for the metal block was 100 degrees Celsius, so it lost heat up to the final temperature of 34 degrees Celsius. From the law of conservation of energy, it requires that all the heat that is lost must be equal to all the heat that is gained. So because the metal block is the only substance that is losing heat, it simply means that all the heat that is lost by the metal block must be equal to the total heat that is gained. So it must be equal to the heat that is gained by the calorimeter and also plus the heat that is gained by water, because the calorimeter and the water, they are only the substances which are gaining heat. And also remember that for this case, we are assuming that no heat is lost to the environment, such that all the heat that was lost by the metal block is equal to all the heat that was gained by both the calorimeter and the water. Therefore, heat lost by the calorimeter is equal to total heat gained. So the heat gained by the calorimeter was 360 joules plus the heat gained by water was 3780 joules. So 360 plus 3780, you will obtain the heat lost, which is equal to total heat gained of 4140 joules. Then Roman 4, they want us to find the specific heat capacity of the metal block. So again, for us to find the specific capacity of the metal block, we'll simply equate the heat lost to the heat gained. That is from the law of conservation of energy, that all the heat that is lost must be equal to all the heat that is gained, provided that no heat gets lost out of the system. That's why we are using a calorimeter, which is highly lagged. So being lagged simply means that no heat or very less heat is being lost to the environment. So all the heat that is lost must be equal to the heat gained. So the substance that is losing heat, of course, is our metal block. So the heat that is lost will be given by mass of the metal block multiplied by specific capacity of the metal block multiplied by the change in temperature for the metal block. Then heat that is gained, we have the calorimeter gaining heat and the water gaining also the heat. So total heat gained will be heat gained by the calorimeter plus the heat gained by water. So mass of the metal block, we are given as 0.15 kg. So 0.15 kg multiplied by specific capacity of the metal block is the unknown or the substance that we are looking for. So C, the specific capacity of the metal block, multiplied by the change in temperature for the metal block, will be given by the difference between the initial temperature for the metal block and the final temperature of the mixture. Then we said whenever we are looking for theta, we are not interested in the negativity. Therefore, to find a positive value of theta, I'll take 100 minus 34. So 100 minus 34, that is the change in temperature for the metal block, must be equal to heat gained by the calorimeter. We had already computed it as 360 joules, then plus heat gained by the water. We had already computed it from Roman 2 as 3780 joules. Therefore, if you take 0.15 multiplied by the difference, that is, if you take 100 minus 34, you'll simply obtain a temperature of 66 Kelvin. So and of course, if you take 360 plus 3780, you'll obtain 4140. So 0.15 multiplied by 66, you'll obtain 9.9. Then of course, multiplied by the specific capacity of the metal block, which should be equal to 4140. So if I make specific capacity of the metal block subject of the formula, I'll simply divide both sides by 0. That is 9.9. Therefore, specific capacity for the metal block will be given by 4140 divided by 9.9, which gives me 41,000. That is 418.2 joules per kilogram per Kelvin. So it is important to note that this answer is correct to 4 significant figures. Next, our second example reads that dry ice is passed into a well-lagged copper calorimeter of mass 0.25 kg. So we have the mass of the copper calorimeter as 0.25 kg containing 0.50 kg of water. So that is the mass of water, 0.50 kg, and 0.02 kg of ice. So that is the mass of ice, 0.02 kg at 0 degrees Celsius. So that is the initial temperature for the ice was 0 degrees Celsius. But because we are told from the question that both the ice and the water were initially in the copper calorimeter, it simply means that if the initial temperature for the ice was 0 degrees, both the water and the copper calorimeter will also assume the same initial temperature as that of the ice. Therefore, because the initial temperature for the ice was 0 degrees Celsius, that is before the dry steam was passed, it simply means that the water was at the same temperature with the ice because they were in the same container. So the initial temperature for the water was also 0 degrees Celsius. But because both the water and the ice were in the copper calorimeter, it simply means that the initial temperature for the copper calorimeter was similar to the initial temperature for the water and that of ice, which was of course 0 degrees Celsius. Then the mixture is well stirred and steam supply cut off when the temperature of the calorimeter and its content reaches 25 degrees Celsius. Of course, the content of the copper calorimeter is simply the ice, the steam, and the water. Therefore, the final temperature of the mixture was actually 25 degrees Celsius. So neglecting heat losses, so this simply means that if there is no heat which is being lost, it simply means that the law of conservation of energy must be obeyed, such that the heat lost must be equal to all the heat that is gained. So find the specific latent heat of vaporization of water if 25 grams of steam, so that is the mass of the steam. Again, we convert it into SI units. So 25 grams into kilogram, I'll simply divide by 1,000 grams times 1 kilogram. So 25 divided by 1,000, we'll get the mass of the steam as 0.025 kg. So it's found to have condensed to water. So remember, steam is condensing to water. Then we are given that the specific capacity of the copper calorimeter is actually 400 joules per kilogram per Kelvin, and latent heat of fusion of water was 3.36 times 10 power 5 joules per kilogram per Kelvin. So because no heat is getting lost, it simply means that from the law of conservation of energy, all the heat that is lost must be equal to all the heat that is gained. So we need to identify the substance that is losing heat and the substance that is gaining heat. So we just look at the final temperature, we compare with the initial temperatures. So clearly you can see that the steam had an initial temperature of 100 degrees Celsius, which is far much greater than the final temperature of the mixture, which is 25 degrees Celsius. So this one clearly shows you that the steam lost heat, that is from 100 degrees Celsius up to 25 degrees Celsius. Then of course the ice, which was initially at 0 degrees Celsius, the water, which was also initially at 0 degrees Celsius, and the copper calorimeter, which was initially at 0 degrees Celsius, their initial temperatures are far much smaller than the final temperature of the mixture. So this one simply shows you that both the copper calorimeter, water, and the ice, they gained heat, that is from 0 degrees up to 25 degrees Celsius. So the substance that is losing heat is only the steam, but the substances that are gaining heat are actually the copper calorimeter, water, and the ice. So heat lost must be equal to heat gained. So the substance that is losing heat is the steam. Then we know that steam usually loses heat in two forms. One, we are going to have the heat lost by the steam, that is in the process of condensation, and two, we are going to have the heat that is lost by the steam, that is after it has condensed to water. So this must be equal to heat gained by ice. Again, we know that ice usually gains heat in two forms. One, we have heat that is gained by the melting ice, that is heat that is used in the process of melting, plus the heat that is gained by the melted ice, that is the ice that has already melted from the solid form up to liquid form, which of course is water. Then plus heat that is gained by the copper calorimeter. Of course, copper calorimeter is gaining heat because its initial temperature is 0, final temperature is 25. So heat gained by the copper calorimeter. Therefore, heat lost by steam, that is in the process of evaporation, that is in the process of condensation, will be given by mass of the steam multiplied by the specific latent heat of vaporization. So the latent heat of vaporization will be given by LV. Then heat lost by water, that is the condensed water. So remember, water condenses from 100 degrees Celsius, that is the initial temperature of steam, up to the final temperature of the mixture, which is 25. So heat that is lost after condensing, after the water has condensed, will be given by the mass of the steam multiplied by the specific capacity of water multiplied by the change in temperature for the steam. Then heat that is gained by the melting ice will just be given by, that is heat that is used in the process of melting. We said that it will be given by mass of ice multiplied by the latent heat of fusion. Then heat that is gained by the melted ice, so it will be given by both the mass of the ice and of course that of water. So we are taking the mass of ice plus the mass of water because remember that ice has actually melted. When ice melts, it forms water. Therefore, the total mass of water will become the mass of ice plus the mass, that is the mass of the melted ice plus the mass of water. Because remember, the final temperature of the mixture is 25. So this one simply shows you that at 25 degrees Celsius, all the ice has melted to form water. Therefore, the new temperature, the new mass of water will be equal to the mass of the ice, that is the ice that has melted, plus the mass of the water that was there, which was 0.5 kg. Then plus the heat gained by the calorimeter will be given by mass of the copper calorimeter multiplied by the specific heat capacity of the copper calorimeter multiplied by the change in temperature for the copper calorimeter. So mass of steam, we already had it as 0.025 kg. So 0.025 kg multiplied by the specific latent heat of vaporization, of course, is given by LV, that is the unknown. Then plus mass of steam, of course, is 0.025 kg multiplied by the specific heat capacity of water, of course, is 4200 joules per kilogram per Kelvin. So that one, even if you are not provided on the question, it's simply a constant value. So the specific heat capacity of water is always 4200 joules per kilogram per Kelvin. Change in temperature for the steam, we'll simply take the difference between the initial temperature of the steam and the final temperature of the mixture, which of course is 100 minus 25. So change in temperature for the steam is 100 minus 25. Then the mass of ice was actually 0.02 kg. So we have it here, 0.02 kg times specific latent heat of fusion. We are given as 3.36 times 10 power 5 joules per kilogram per Kelvin. Then the heat gained by the melted ice. So remember, the melted ice, when ice melts, it forms water. Therefore, the total mass of water now becomes the mass of the water that was initially in the calorimeter plus the mass of the ice. Because remember, the ice has actually melted to form water. Therefore, the new total mass of water will be equal to the mass of the water that was initially in the calorimeter plus the mass of the melted ice. So remember, when a substance changes its state of matter, actually mass remains constant. Therefore, even after melting, the mass of the melted water or the melted ice will be equal to the mass of the ice, which was in solid form. Therefore, the total mass of the water will be equal to the mass of the water that was initially in the calorimeter plus the mass of the water that has melted from the ice, or the mass of water that has changed from the solid ice into the liquid state. Therefore, the total mass of the melted ice will be the mass of the water, which was 0.5, plus the mass of the melted ice, which has actually melted to form water. So 0.5 plus 0.02 kg. Then specific capacity of water, of course, is 4200. Then the change in temperature for the ice is usually we'll simply take the initial temperature for the ice. Of course, also the water was at the same initial temperature of 0 degrees. Then we subtract from the final temperature of the mixture, which is 25. Again, when you are subtracting, you simply take the larger value, the smaller value, subtract from the larger value, because we don't want a negative value of theta. Therefore, I'll simply take 25 minus the initial temperatures of both the ice and the water. So 25 minus 0. Then mass of the copper calorimeter, of course, was 0.25 kg. Then times specific capacity of the copper calorimeter, we are given as 400 joules per kilogram per Kelvin. Change in temperature for the copper calorimeter, initial temperature for the copper calorimeter was 0 degrees, final temperature 25. So the difference in temperature, for us to get a positive value, we'll get 25, then we get 0, we subtract from 25. So 25 minus 0. So actually the key point here, you have to be very careful here. When you are computing, that is MC theta for the melted ice, remember to take, to put into consideration the mass of the melted ice. So the total mass, you'll simply take the mass of the water that was initially in the calorimeter, which was 0.50 or 0.5 kg, plus the mass of ice. Why? Because the ice has actually melted to form water. So that water that has been formed from the melted ice, it will actually combine with the water that was initially here. Therefore, the total mass of water will be 0.5 plus the mass of the melted ice, which is 0.02. So that's why I'm taking 0.5 plus 0.02. So you have to be very careful with this concept. So if you take 0.025 multiplied by LV, you'll just get 0.025 LV. Then 0.025 multiplied by 4200, you'll simply obtain 105. Then of course 100 minus 25, you'll obtain 75. Being equal to 0.02 multiplied by 3.36 times 10 power 5, you'll simply obtain 6720. Then if you take 0.5 plus 0.02, you'll simply obtain 0.52. Then of course times 4200, then multiplied by 25 minus 0, you'll simply obtain 25. So 0.05, 0.0, that is 0.25 multiplied by 400, you'll simply obtain 100. Then 25 minus 0, you'll simply obtain 25. So of course 0.025 LV will just remain as 0.025 LV. Then 105 times 75 will obtain 7,875. Then 6720 will just remain as 6720. Then 0.025 multiplied by 4200 times 25 will obtain 54,600. Then 100 by 25 will obtain 2,500. So I want to collect the like terms. So I want to remain with 0.025 LV on the left hand side. So this value will move towards the right hand side. Of course, when it crosses equal sign, it becomes a negative. So we'll have 0.025 LV being equal to 6,720 plus 54,600 plus 2,500, then of course minus 7875. So negative because it has crossed the equal sign. So if you perform this operation, that is 6720 plus 54,600 plus 2,500 minus 7875, you'll obtain 55,945. So if I want the value of LV, I'll simply divide both sides by 0.025, so that LV will be equal to 55,945 divided by 0.025. So you perform this quotient, you'll obtain that is 2,237,800 joules per kilogram. So that is the latent heat, the specific latent heat of vaporization of that particular steam. Lastly, I have an exercise that I recommend you should try at your own free time to get the understanding of the concepts that we have just learned. Of course, if you have any challenges in handling any of the questions, feel free to drop a comment specifying the question that you need help in, and as usual, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that shortcuts cut dreams short. The quote is encouraging us to channel our energy and efforts towards long-term benefits as opposed to short-term rewards. Most people have lost great opportunities in life just because of being myopic, egocentric, and impatient. I'm here to encourage you to do things the right way, regardless of how difficult it might seem to be. Remember that in order for you to make your life easier, you must do the hard things. Otherwise, if you choose to do the easier things, then expect your life to be hard forever. And lastly, recall that the harder you work for something, the greater you will feel after achieving it. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you will get notified. If you know any student or anyone that you honestly think could benefit from this content, kindly refer them to Kind Tuition Academy or share my link to them. Until next time, this is Kind Tuition Academy. Thank you very much.